In this video, we're going to prove a big theorem about subgroups of cyclic groups. So let's suppose that G is a group. And in fact, let's suppose it's a cyclic group. And of course, as always, a cyclic group means that G can be generated by some single element of the group. So that's for some A and G. Okay, so G is the cyclic group generated by A for some A and element of the group. The theorem that we're going to prove is that every subgroup of G is cyclic. So if G is a cyclic group, then every subgroup of G is cyclic. That's what we're going to prove in this video. Now, before getting into the proof, I just want to come over here and do a little bit of thinking. So let's make this my thinking space over here. I find this useful to do sometimes when I'm about to embark on a difficult proof. So in my thinking space, I'm just going to draw myself a picture of what G might look like. So one thing that we've talked about before is that if G is the subgroup generated by A, or if G is the group generated by A, then that means that G only consists of powers of A, because by definition that set or that subgroup is the set of all A to the n such that n is an integer. It's the set of all powers of A. So if that's the case, then G is going to look like one of these pictures. It's either going to look like a set of a bunch of powers of G, or powers of A, sorry, where there are no repeats. So remember, you have to have both positive and negative powers of A, and of course the zero power, which is the identity. So G either looks like this, or it looks like this. You have some powers of A, and then eventually you circle back to A to the n, which is equal to A to the 0, where n is the order of A. Okay, so either A has infinite order, or A has finite order. And in each case, we have a pretty good picture of what the group looks like. Now, let's suppose that I just start picking off some elements of this group to be in a subgroup. So let's say I have this one, I have this one. Let's see. So I'm just trying to think what would make a coherent choice, just to give an example. Let's say we have that one. So one point I want to make here is that we can't just go randomly picking out elements to live in a subgroup. Things have to be kind of systematic. So let's just say I know that I have the elements that are circled in purple. And I'm going to show that I have to have actually quite a few more elements than that. So one thing that I know is if I have, for example, a to the minus 2, then I have to have the inverse of that as well, which means I have to have a to the 2 in there. And then if I have a to the 2 and a to the third power, then I also have to have a to the third times a to the negative second, because, well, I actually know I have a to the negative second in there. I don't have to argue that again, which is equal to a to the first. So I have to have that element as well. And of course, I always have to have the identity. So it turns out I'm going to wind up having all of my elements in this subgroup. So just knowing that there are certain elements in my subgroup, I can make certain inferences about what other ones have to be there, and that's going to be part of the proof. So anyway, I don't have to have all of the elements, though, in order to have a subgroup. I could have some proper subset. So I'm going to circle another one in red and say, let's suppose I have this one, I have this one, I have this one, of course, because I must have the identity, and I have this one. So I could have all of the even powers, and that would be fine. If I take any two even powers and multiply them, I still have an even power of A. The inverse of any even power is still an even power. So what I have in red makes a perfectly fine subgroup as long as I continue that way. So I would also have to have a to the 6th, a to the 8th, a to the 10th, and so on. So what we're going to do in our proof is we're going to look at the least positive power of A that's represented in our subgroup. And we're going to prove that that determines the entire subgroup. In other words, if I can identify the least positive power of A that is in my subgroup, then my subgroup is going to be equal to the cyclic subgroup generated by that power, where K is the least positive integer with A to the K belonging to H. So that's going to be the strategy of the proof. All right, so let's come over here and see if we can write this up. All right, so here's the proof. Let's let H be a subgroup of G, and then we will show that H is cyclic, meaning that there exists some X in G such that H is the cyclic group generated by X. Now you notice here I said X is in G. Of course X would be in H as well, because in order for H to equal the group generated by X, X has to live in H. But I'm just saying that we can identify some element of G for which H is the cyclic subgroup generated by that element. Now what I want to do at this point is I want to let K be the least positive integer such that A to the K belongs to H. But before I can do that, I have to think about this for a minute. Is there actually such a positive integer? Because I'm not sure that there has to be. So is there some K, a positive integer, such that A to the K belongs to H? Well, if not, I think it's actually possible that there might not be, because what if I had a subgroup consisting only of A to the 0? And that's it. And A to the 0, because A has maybe infinite order, it doesn't go by any other name with a positive exponent. So I could have just A to the 0, and there is no such K. So if not, then I claim that H is equal to just this. Okay, but I need to prove this because, well, there is another possibility. I could have 0, and I could also have negative exponents. But I think that's going to turn out to be false. Okay, so here's why. If A to the K, let's not use K, let's use some other letter. A to the L belongs to H. For some L less than 0, then, because H has to contain inverses, it's a subgroup. A to the negative L also belongs to H. And negative L is greater than 0. Okay, and I claimed already that there is no positive integer K such that A to the K belongs to H. Okay, so that means that, so no negative power of A is in H either. So H contains only the 0th power. Only A to the 0, because that's the only power of A that can be in H, and the only things that are in G are just powers of A. G is cyclic. All right, so H is just the cyclic subgroup generated by A0, which is also just the set containing only the element A to the 0. All right, so that's one case. The other case is that there actually is a positive exponent that belongs to our subgroup. Okay, so just to make sure we keep our orientation here, this is case 1. This is case 1, and now we're in case 2. So case 1 was that there is no positive exponent such that A to that exponent is in our subgroup. Now case 2 is that there is a positive exponent for which A to the K is in our subgroup. So if there is some K, a positive integer, such that A to the K belongs to H, then, well, let's let M be the smallest such positive integer. In other words, the smallest positive integer such that A to the M belongs to H. Okay? So what we're going to prove, this is a claim. I'm going to prove that H is exactly the subgroup generated by A to the M. But now I have to prove this. I can't just claim it and then leave it alone. I have to give some argument for why this is the case. So to prove this, I'm going to remind myself these are two subgroups of our original group G. And in fact, they're subsets. So to prove that they're the same, I'm just going to do the old usual straightforward thing of proving that each is a subset of the other. That's going to be my strategy. So I think I'll start with supposing that x belongs to the subgroup generated by a to the m. Okay, now remember that a to the m, that subgroup is just the group of all powers of a to the m. So it's the set of all elements a to the m raised to the n, where n is an integer. That's what it means to be the cyclic subgroup generated by that thing. And I can rewrite that just using properties of exponents as a to the mn, where n belongs to the set of integers. So we'll show, so first of all, so then x belonging to the set has to equal a to the mn for some integer n. So now I need to show that x also belongs to h. Okay, well, what do we know? We know that a to the m itself belongs to h because that's what we assumed about a to the m. We know a to the m belongs to h, and h is closed under multiplication and taking inverses. So we know that x, which is a to the m to the n, has to belong to h. Since this element, a to the m to the n, is either a product, just by definition, it's a product of a to the m's, a product of copies of a to the m inverse, a product of copies of that, or the identity. Okay, so actually here I didn't even really use the fact that this could be rewritten as a to the mn. I just used the fact that every power of a to the m has to belong to a subgroup if that subgroup contains a to the m. So that means whatever x is, it has to belong to h. Therefore, this subgroup has to be a subset of h. So just reviewing here, the idea here was everything in that subgroup, everything in the subgroup generated by a to the m is a power of a to the m, which is in h, and thus must belong to h. So now we'll prove the other direction. This will be the grand finale for this theorem. Okay, so other direction. Let's use blue for this one. Sorry, I'm kind of picky about my colors. There we go. All right, so other direction. Okay, so now I need to show that h is a subset of the cyclic subgroup generated by a to the m. Suppose that x belongs to h. We'll prove x belongs to the subgroup generated by a to the m. All right, so, well, the fact that x belongs to h right now doesn't tell us a whole lot immediately, but it does tell us that, well, since x belongs to h, which is a subgroup of G, and that means that we know x belongs to G, and we know that G consists only of powers of A. So since G consists only of powers of A, we know x has to be some power of A. So what shall we call it? I'm kind of running out of letters here. I think I'll use a to the j. X equals a to the j for some integer j. Don't know if it's positive or negative, so we're going to stay agnostic on that. It could be 0 too. It's just x has to equal a to the j for some integer j. All right, I'm going to prove that a to the j has to belong to this subgroup. So now remember, this subgroup consists only of, let's make that a set bracket there, only consists of a to the mn, where n is an integer. So it's only the powers of a where the exponent is a multiple of m. So I need to check that j is actually a multiple of m. And how do we check whether something is a multiple of some other number, or whether m divides j? The way that we do it usually is we use the division algorithm and get a remainder, and we try to show the remainder is 0. That's kind of a common strategy with this type of proof. So since m is a positive integer, by the division algorithm, there exist integers q and r such that j is equal to mq plus r, and again r satisfies that condition of being a remainder, so 0 is less than or equal to r is less than m. Okay, but then what do we know? So again, I know that j is equal to mq plus r, and I know that x is equal to a to the j. So I'm going to use this expression for j to rewrite x in slightly more useful terms. So we have x to the j, or sorry, not x to the j, x equals a to the j, which is equal to a to the mq plus r. And now I'm going to do a little bit of algebra over here. So we're going to use our properties of exponents to rewrite this as a to the mq, which is also a to the m to the q, times a to the r. And what do we know here? We know that a to the m to the q, this is a to the m. A to the m belongs to h, and then I'm just raising that to a power. So let's write down what we know here. We know a to the m belongs to h. So a to the m to the q, by the same argument I just did earlier, any power of that also has to belong to h. And we know that x equals a to the j. That belongs to h, because that's just what we assumed. We assumed that x belonged to h. So, okay, so just a minute. Let me just keep track of some things here. So we know this belongs to h, and we know this belongs to h. So I claim that this too will have to belong to h. And the reason I'm going to use there is that I know this belongs to h, I know this belongs to h, so I know that the inverse of this has to belong to h. So I'm going to multiply both sides on the left by the inverse of this element, giving me that a to the r is equal to the inverse of this thing, which is in h, times this thing, which is also in h. So this will have to belong to h. So let's write that down. All right, so we have a to the j, which is x, is equal to a to the m to the q times a to the r. Now let's move it down a bit. Multiplying on the left both sides by the inverse of a to the m to the q, I get a to the m to the q inverse times x equals a to the r. And since a to the m to the q inverse belongs to h, since h is closed under taking inverses, and x belongs to h, a to the r belongs to h. But wait a minute. What did we assume here? We know that r is less than m, and we know that m is the least positive integer. I'll just call it the least positive power of a that is in h. So if I have this other thing, a to the r, that is also in h, then since m was the minimum positive power in h, that means that r can't be positive. R has to be 0. So r has to be 0. So what this means is that, therefore, x is equal to a to the mq plus r, but r is 0, so that's just a to the mq. And that's a to the m raised to the q, which we know belongs to the cyclic subgroup generated by a to the m, because this is a power of a to the m. So what do we know? This means that x, which we only assumed was in h, has to be in the cyclic subgroup generated by a to the m. Therefore, h is a subgroup of A to the M. I should say subset probably, but I know it's a subgroup as well because H is known to be a group. So since A to the M, that cyclic subgroup is a subgroup of H, which we proved earlier, and H is a subgroup of the cyclic subgroup, that means that H has to be the cyclic subgroup. And since H was just any old subgroup of a cyclic group, therefore we conclude, this is the grand finale, every subgroup, good lord, my pen is skipping like crazy, every subgroup of a cyclic group is cyclic. And that's it. Without further ado, that's the end of the video.